I want to complete, well, not complete, but talk about file systems. This is chapter 11, and next week there are several things that I want to do, sort of road ahead. If you want to do more systemsy kind of work, I want to talk about show and tell, and then a review. Okay, so these are things that I have planned for next week. Depending on, I may, if I don't complete it all today, I may take a little bit of time on Tuesday to do that. So today, I mean, so we've seen the disk and the disk scheduling and so on, and now we're going to see the software complement to storage system, that is a file system, and you've all heard the term booting, right? What does it mean when you say boot up a machine? What does it mean, Owen? So where does the term booting come from? Any idea? Nick? Chandler? Brad? Michael? Bootstrapping, so sort of picking oneself up through the bootstrap, right? That's where it comes from. Literally, that's where it comes from, and that's what an operating system does. Because when you power it up, what is the processor capable of doing? What is the processor capable of doing, Brad? Wow, wait a minute, processor, what is it capable of doing? Executing a program, right? Basically, the only thing that the processor is capable of doing is running a program, right? There's no other smarts. Well, it's plenty smart that, but it has no other smarts, right? Other than just running a program. But when you boot up the machine, what program should the processor run? Alazar. Yeah, so what you need is something that is statically known that, oh, this is the program that I have to run every time I power up, right? And that program is the boot program, right? So the basic program that is run when you power up a machine, that's the boot program. So there's a well-known address where the PC is going to start, you initialize the PC to some value when you power up, and at that PC location, you got a program, that's the boot program. And as I said, it is in read-only memory, right? So ROM that is in your in your machine, and that program runs. And what does that program do, Alazar? Raise your voice a little bit. Yeah, so you're saying a lot more smarts for the boot program than what it is, but essentially what you really want to do is, you're sort of picking up on your bootstrap, right? The lowest thing that you're doing is start up the machine, and you run the little program that says, okay, let me initialize all the devices, okay? And once I initialize all the devices, let me then call the next level up, which is what Alazar is saying. I don't know what that next level up is. It may be, an operating system, it may be a control program, whatever it is, right? Depending, even your cell phone, right? Or a printer, every one of those devices has goes through the boot process, right? And in the case of a printer, there is no sophisticated operating system or anything like that, but it still knows what it needs to do. What are the functionalities associated with the printer? And so there is a program, the control program for the printer, that gets to run through the booting process, right? And and have you heard the term BIOS? What is BIOS, Shane? Basic input-output system. That is the very basic thing, as it suggests, in the PC world that is run when you boot up the system. So when you go from the ROM, the next thing up is BIOS, right? And BIOS is a basic input-output system that says, okay, now I have to make sure that I can talk to all my devices, and we know that in the context of devices, you've got device registers that have to be initialized and things like that. So the basic input-output system is going to say, test out all the devices and say, well, is this mouse capable of generating an interrupt? Is the keyboard capable of generating an interrupt? All those kinds of things, that's what goes through before it says, okay, the basic input-output system works, and now we can then give the control up to the next level in the software stack. So there is a whole bunch of software that is stacked on one on top of the other. And Emily had a great question. So when I say software stack, does it really mean a stack? You know, because when you think about a stack, there is this sort of a push down and pop mechanism, right? So you push things in and then pop the first thing out and so on. And you know, in some sense, it is similar to that. It is not exactly that, but in terms of functionality, all of these software layers stack one on top of the other. There is the boot program that is in the ROM. Next level up is the BIOS, and next level up is the operating system, right? And similarly, when you think about the protocol stack, which is inside the operating system, you have these different layers of the protocol stack, right? And so this power of abstraction is very good in that you're able to sort of compartmentalize every one of these levels of abstraction. So if you think about this, so there is a boot program, and then on top of that is the BIOS, and then on top of that is the operating system. But we know that the operating system is itself a big beast, right? There is the scheduler, there is the VM manager, and there is the protocol stack. And if you say, look at the protocol, that again is you can sort of blow it up into the 5 layers that we talked about. There is the app layer, the transport layer, the network layer, the link layer, and the physical layer, right? So you can see that there is the power of abstraction that, you know, when you think about the boot program, it's just a simple program that is going to start running because the processor is capable of doing only one thing, that is execute instructions. Then it calls one level up in the boot process. At the end of this, it's going to say, well, run the boot BIOS now, because I want to test out the I/O devices, whether they're all sound and everything. And once it is convinced of that, it runs the operating system. So you can see this level of abstractions here. So then, if you blow up each one of these levels, you find that there's a whole bunch of components that may be laid out horizontally in terms of functionality like this, right? The CPU scheduling functionalities horizontally, you know, it's sort of, when I say horizontal, they are at the same level. It's not a stack, right? So scheduler can talk to the VM manager may. It's sort of a, you heard this term peer-to-peer. So it is peer-to-peer communication as opposed to going top-down or bottom-up, right? So in this case, it is peer-to-peer. The scheduler may talk to the VM manager may talk to the scheduler, and the VM manager may talk to the protocol stack, and so on. But if you look inside the protocol stack, then the organization is like a stack, right? Because the application layer is the one that says, do something for me. Transport layer says something to the network layer. Network layer does something to the link layer, and so on. And so there's information flow going down this way and information flow coming up this way. Okay, so that's is that idea clear, Emily? They are not physically on top of each other. It's just that they're the functional modules, and the way they interact with one another is this sort of hierarchical manner, right? That's the reason why it is called a protocol stack. Okay, so we talked about how you go from booting to the operating system, and we're going to look a lot more of those details later on. But what I want to do now is just talk about the file system. So once the system is booted up and you have it running, then your persistent data structures, persistent files, and so on and so forth, they're all on your hard disk. And what we're going to look at is how do you design the software abstraction called the file system? What are the sort of elements of the file system? So what we're doing is we're adding one more box here, a file system box, and trying to understand what are the elements of the file system. What is the software subsystem called file system? What does it need to do in order to access the hardware device, the disk, and organize information on the hardware device, and so on, right? And one of the first thing that you have to worry about is how do you allocate space on the storage device. And last time when we looked at the disk, we saw that the disk is composed of these platters, and platters are stacked one on top of the other, and each platter may have a couple of surfaces, and so there is recording of information that can happen on both of those, and the surfaces contain a whole bunch of tracks, and we said that, you know, if you look at all the tracks, which are the corresponding tracks on all the surfaces, they form a logical cylinder, and we talked about why the idea of a logical cylinder is meaningful, because Chris, why is the idea of a logical cylinder meaningful? Any idea? Ryan? Mikey? What is the idea? Why is the idea of a logical cylinder meaningful? Yeah. Right. So the idea is that, you know, if you look at we said there are multiple platters, right? And so the multiple platters, if you think of these as the platters, then, you know, the read-write head assembly is mounted on a single mechanical device, right? And the whole thing moves in and out, right? The whole thing moves in and out of the disk assembly, and when it does that, so when it is positioned at a particular place, then all the corresponding tracks on all the platters are aligned, right? And that's the reason why we talk about the cylinder, and the point is that, you know, it is much more efficient. From, you know, why is it much more efficient? It's called the seek time, right? The seek time is the most expensive part of accessing a storage device, and because why is that the most expensive part, Jen? Mechanical, right? So it's mechanical, and that is going to be expensive, and so you want to reduce the amount of mechanical motion, and that's why a logical cylinder makes sense, right? Because once you've positioned your head assembly, then you are in position to read all the tracks, right, of all the surfaces at the same time. Not at the same time, but, you know, you have to sequence it, but you don't have to have mechanical movement of the head in order to do reading of all the tracks. Is that idea clear? Okay, and that's the reason that the logical cylinder makes sense. Yeah. Lots. No, much more than that. So when we looked at, you know, the recording density is very, very fine. So remember the size of the air gap, and so the recording density is very fine. So on the orders of several thousand tracks you can lay out, depending on the size of the platter, right? And so it's a lot of. I mean, I can look it up. I mean, you can also look it up. You know. Oh no, it is a small number of tracks, a huge number of tracks, and that's the reason why it is expensive to move the head assembly. And yeah, Jen. Well, the head assembly doesn't move very fast. You know, it is mechanical motion, and you know, one of the modern disks are very complicated these days, right? And so we talk about seek time being expensive, and it's absolutely true. But a lot of times the disk assembly is very, very smart, okay? And I mentioned that disk scheduling, as we learned it, is I made it look like it is a piece of the operating system, right? Because disk scheduling algorithms. But today, a lot of that is moved into the disk device itself. And when you talk about a USB drive, then all you are doing is talking USB protocol, a serial bus protocol with the device. And internally, the device is doing a lot of things. And one of the things that it does is it says, well, the next track that I'm at a particular location, and the next track I'm going to read is such and so, and so it can actually and also it knows the track that the sector that it wants to read. So as it is moving towards the particular track, the one part is the seek latency, the other part is the rotational latency, right? And so the disk will actually start changing its speed in order to make sure that by the time the head arrives at that particular track, it's very likely that the sector is also under the track, so that it can optimize on the rotational latency. Lots of smarts are going on inside the disk technology. So you know, it's variable speed in terms of how it moves in and out, and in terms of how the revolution we talk about RPM, right, to make life simpler for us in terms of calculating transfer rate and so on. But RPM, even though it may say it is 1500 RPM or 15,000 RPM, it is not that it is always spinning at that speed. Okay, it can change its speed, and modern disk drives, as you know, stop spinning, right? Why does it stop spinning? Save energy. So when you're not accessing the disk, it is just stopping its spinning also. So lots of things are going on inside the disk that's beyond the scope of what we want to get into. Okay? So what we want to do now is think about the allocation policy. Given that we have to allocate storage space, how do we do that? And this has a lot of similarity, as I mentioned earlier, to memory management policies, right? And so what are the things that you would think are important, figures of merit, from the point of view of disk allocation, storage allocation? What are the things, what would you say are things that you have to think about in terms of storage allocation? Meaning, think in terms of high level, that you have an application that wants to read and write files and so on. So from that point of view, what do you think are the important characteristics that you want in terms of how do you allocate space on the storage system? Okay, so size of the file, right? So is the size fixed of a file fixed? Not necessarily. It can grow, right? So one figure of merit is, does it allow for easy growth of file, right? That may be one figure of merit. Any other figure of merit that you can think about, Shane? Pardon me? Naming is part of it, but I'm not talking about naming at this point. I'm talking in terms of if I have a file system that I want to build, and I want to think about, just like we did memory management, right, in the context of physical memory, virtual memory and physical memory. Similarly, if I'm thinking in terms of how do I allocate space for files that I want to store, what are the things that you do with a file? So think about, what do you do with a file? Read, write. So when you read, write, do you read randomly or sequentially, right? So when you do sequential read, then one of the figures of merit then becomes, is the storage allocation policy mirroring the fact that I may have the need for fast sequential access, right? Do you do random access to a file anytime? No, random access. And from an application point of view, do you do random access to a file? Ever? Matt? You don't think so? Anyone think you do random access to a file? Well, what is the application characteristic which calls for random access to a file? You do that all the time. When I tell you, you'll see, oh, wow, sure. Oh, that's one example. So you're always thinking of movie. Anything else? No, not memory. This is only about storage space, right? Olga, any other example of an application level thing that you might want to do a file that may cause random access, Ron? That, when you're opening different folders, you're looking at different files, not, given a particular file, what are the things you want to do? So I think, what you said is absolutely true, that you are going to, if you're watching a movie, you may fast forward and but even if you do that, fast forwarding is like saying, well, get me to, it's almost like doing a new read access, which is to a different place. But what is another random access? Alazar, can you think of? Well, program is in memory. You already loaded it into memory. So we're talking about file access. Yeah, when you get it from the disk, you're building the entire program, memory footprint, right? So you do need to read the whole file, and there you're doing sequential access, because a whole file you're reading in the disk image, and then saying how to build the memory footprint for that. Think about search. Don't you do searches? You do all that all the time, right? You search when you're editing a program or looking at files, you look for something, you're searching. When you're searching, you are doing random access. You don't know where it is on the file, right? And that's an example where the application level, you're doing something that has to be mirrored in terms of performance at the storage level, right? So random access, sequential access, growth of file, anything else? these are good starters, right? And so these are the things that you have to worry about in terms of so these are different schemes, but the figures of merit I've just mentioned. Fast sequential access is one thing that you said, fast random access, the ability to grow the file. And the other things are more to do with, the first three are the things that you guys told me about, which is from the point of view of an application, right? What are the things that the application cares about? Those are the first three things. And the bottom two things, what do they correspond to? Yeah? Yeah. Well, actually both of these, this is efficient, easy allocation of storage. What does that pertain to? It doesn't anything, has nothing to do with the application, but what does it have to do with, why is this a figure of merit, easy allocation of storage? Think in terms of what I said about what a good characteristic of an operating system is. What is a good characteristic of an operating system? Jen? Doesn't take much time. So whatever is the operating system activity, you want it to be done efficiently but very quickly, right? Because if a CPU scheduler takes hours to schedule the next process, you're not going to be happy, right? Because you want that to get its work done very quickly and go away. Same thing goes for storage allocation, right? So if I want to allocate storage for a file, then that should be done very quickly, so that it doesn't take a lot of time. And the last thing is, you may have a lot of space on your disk. Peter mentioned fragmentation. So what do you mean by fragmentation? Contiguous. So if you think about it, all of these things, if we say fast sequential access, that suggests that you would like the contents of a file to be contiguous, right? And so when you want it to be contiguous, what is the hierarchy by which you will go with contiguous allocation on storage device, like a disk? What are the things that you would do? If I have a file that I want to allocate and I want it to be contiguous, how would I go about doing it? I'm just, don't think about data structures or anything, just logically. I have a disk, it's empty, nothing there, right? And I want to allocate a file. So, and if I want it to be contiguous, what will I do? Space on the same track if I can, right? Because that's contiguous. If I run out of room on that same track, where will I go? Next track on the same cylinder, right? And if I run out of space on the entire cylinder, then I'll go to an adjacent cylinder, right? So that's the way you would try to do contiguous allocation, so that when you think about sequential access, it will get you very good sequential access. Okay, and so when we talk about allocation of storage, there's a coupling between the application level requirements, okay, and the system level requirements. One is how quickly the operating system can allocate something and get out of the way, and also efficiency of utilization on the storage device. I mean, you have lots of storage, but the two things that you want to worry about, I mean, you can always run out of storage, right? So you can write a program that continuously writes files, and eventually you run out of storage. If you write a busy program that continuously allocates storage space, it'll eventually run out of space. And these days, we are storing movies on our disks and so on. Takes up a lot of space. A gigabyte for a movie, and so pretty quickly you can run out of space. And so efficient space utilization on the disk is another important figures of merit. So these are the things that you have to worry about when you think about what is the right allocation policy that I want to have for storage space on the disk. Okay, and we'll look at several different allocation policies. The first one is what is called contiguous allocation, which mirrors the fact that you want fast sequential access, right? And so what you're going to do is exactly what I said. That is, you allocate things in a set of cylinders and so on. And then we will talk about, for each one of these, and for each one of these things, we'll talk about what are the pros and cons with respect to the figures of merit. Everybody with me here on this? Okay. So let's first look at contiguous allocation. So the idea is, just like in the case of memory management, the operating system had this page table, right, which is actually giving you a way by which you can map the application's view of its memory to the physical view of where it is in physical memory. That's the operating system's job, is to keep that mapping, right. Similarly, from the point of view of the application in the file system, you have a file, and let's call it foo, and so you need to know where exactly it's going to be on the disk. So what you need is a directory, and the directory contains all the files that is in your file system, and this is what Ron was talking about, that you have multiple files, right, and all of those are in a folder, and that is what is called a directory. So you got a directory, a bunch of files in it, and in contiguous allocation, what we're saying is we're going to split this world into small sized files, medium sized files, and large sized files. Remember the allocation policy, a memory allocation policy called fixed partitions? Remember that? Okay. How did we do that in fixed partitions? What is the right? And what we're going to do is we're going to say, well, if somebody asks for 4K, and if I have fixed partitions that says, I've got 8K partition, a 2K partition, and 4K partition, and somebody asks for 6K, then you're going to give that program an 8K partition, because that's the size that encompasses your request, right? And that's the same idea here. That what we're going to do is we're going to split the storage space into saying that, well, I'm going to break the world of files into 3 classes. Either they're small files, or medium files, or large files. Okay, and I might say that a small file is 1 cylinder, medium file is 10 cylinders, and a large file is 100 cylinders. Right. So I make that division, and once I do that, when you come along and say I want to create a file, then I'm going to say, well, is it a small file? One of these classes, and depending on that, I'm going to allocate storage for you. Okay, and in the case of fixed size partition in memory management, the nice property of that memory management scheme is that the data structure that the operating system needs to maintain is very simple, right? What is the data structure that you would need? Maba, do you remember? What is the data structure that you would need for a fixed size partition? Yeah. Pardon me? An array of what? You just need a bit vector, right? That says, I have 4 of these 8K partitions, and 4 of these, 2 of these 6K partition, and so on. So I just need a bit vector whether that partition has been allocated or not, right? And that's all that you need in terms of data structure. Is very simple. That's the same advantage that you get with this contiguous allocation, that the data structure that the operating system needs to maintain is much simpler. It's only an array of bit vector that says suppose I have 100 of these medium-sized partitions and 1,000 of these large and maybe 1,000 of these small, then I have bit vectors for each one of those categories of storage sizes, right? And as I'm making allocation, I can say, well, this is taken, and so on and so forth. Okay, is that idea clear? How this contiguous allocation would work? Okay. Now, what is the problem with fixed-sized partition in memory management? You thought a file was small, and you allocated it to be a small-sized file, and now it wants to grow, right? Because one of the figures of merit we said is allowing growth. This is good for sequential access and for random access also, because it is all contiguous, and therefore it is going to be good for those properties. But from the point of view of growth, we have a problem, right? If it grows beyond the size, then I can either say, well, too bad, or I may have to copy the whole thing into another medium-sized file and change the location of that particular file, right? And that's one of the problems with contiguous allocation. Everybody with me here? It's good for sequential access, good for random access, but not good for growth. Now, one way to fix this, how can I fix this? How can I fix this? I like the fact that, from the application point of view, I'm doing random access, I'm doing sequential access. But growth of a file is an important issue also, and I don't want to do this heavy duty thing of saying, well, this file has grown too much, I'm going to copy it over to, that's too much work to do, right? So is there some simple quick fix that you can do? Eugene? First of all, you hope that this situation that I'm mentioning is an oddity, right? It's not something that you expect to happen too often, that you've allocated space for a file and it grows beyond its expected maximum size. So hopefully those are not things that happen too often, okay? So what you need is, I mean, always one of the principles in system design is optimize the common case, okay? The uncommon cases, you don't mind paying a little bit of an overhead, okay? So long as the common case works really well. And the common case will work really well here because we are making sure that you guessed right in the beginning in terms of what may be the size of the file and so on. Okay, so we have to take care of the uncommon case. Yes. Yeah. Yeah. Right. So that's exactly what is done in this contiguous allocation with overflow. So the idea is that you normally assume that we're going to do, so this is the free list for contiguous allocation before we leave this. So free list is going to say, here is a free block, and here is another free block, and here is, all of these are free blocks, of course. But these are free blocks which says how many contiguous cylinders are available in this free block. It says that there's one contiguous cylinder available and two contiguous cylinders available and so on. So this is the way we've broken up. And now following up on the suggestion with the growth of the file, what we're going to do is, so what we're going to do is, I don't have a foil for that, but basically allocation of the overflow that says this is the size of the file. If it grows beyond this, there's overflow area. And I'm going to say, well, additional space I'm going to allocate out of that overflow area. So whenever you access, let's say that you're contiguously accessing a particular file and you find that, it has grown beyond its maximum capacity for that allocation, then, as he pointed out, you're going to go to the overflow area to find where the rest of the file is. Maba? We're not even moving, right? So when you're allocating, right? So when you grow a file, let's say that I gave you one cylinder for your file size, and you start writing, and it becomes one cylinder plus a track, right? I have to allocate the track somewhere, so I'm going to get it out of the overflow area in order to do that allocation. So that information has got to be kept. So we're making the data structure a little bit more complex, right, compared to the contiguous allocation. But that complexity satisfies one of the user level requirements in terms of growth of a file. Okay, so the next thing that so what is the downside of a fixed size partition of memory management? Abhishek, do you remember? What is the internal fragmentation? What is that? Right. So if you're always allocating something that is bigger than what you need, right? Which essentially means that some portion of it is going to be unused, right? And that is a problem with contiguous, with fixed size partitions. That's the same problem with contiguous allocation also. But is that the only problem that fixed size partition has, Ron? Oh, the overflow can be as big as you want, right? It is just a whole bunch of cylinders. No, you don't have to. So the idea is, right. So you see, so let's say that here is the disk, and these are all the surfaces, and let's say that I'm going to use a particular cylinder in this, right, for a particular file, okay. And what I'm going to say is that there is, there are additional areas which I'm going to call the overflow area. So this is the overflow area. This is the overflow cylinder. And so there's a whole bunch of I may have a set of cylinders available as overflow area. So if I run out of space on this cylinder for this file, I'm going to basically allocate a track from one, or maybe a cylinder from one of the overflow cylinders that I have, and I have a whole bunch of them. Okay, that's the idea behind that, right? Pardon me? No, 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 no. They're all distinct cylinders. So see, the granularity of storage allocation is usually in cylinders, simply because that's more efficient, right? In terms of data structure, I said that logically for purposes of optimizing seek time and rotational latency, you want to allocate things in units of a cylinder, okay? And so you have a whole bunch of overflow cylinders, so you can always allocate that overflow cylinder. But you have to keep that information around in saying that, well, this particular file uses this set of contiguous cylinders plus this overflow cylinder, which may be anywhere in that data structure. Okay. So where was I before you asked that question? Oh, I was asking, in addition to internal, you said internal fragmentation is a problem. So is that the only problem with fixed size partition? John, with fixed size partition memory management, is there any other problem that you can think of? We said internal fragmentation. Brad? What are the two kinds of problems that you can come up you can potentially have with memory management? External, right? There's internal, there's external, and what is external, Eugene? No. I mean, we're not even thinking about contiguous with overflow. Just think about contiguous allocation. And I'm saying contiguous allocation, the corresponding thing in memory management is fixed size partition, right? In fixed size partition, we said one of the problems is internal fragmentation. And I'm asking you now, what is external fragmentation? What is external fragmentation? No. Just think about memory management, right? So what is holes in memory and they're not together. So there are distinct free spaces available in memory, but they're not contiguous, and that's an issue because when you need to allocate memory, you're always looking for a contiguous piece of memory, right? So you're saying I want a 6K of memory, and if I have 6K available but they're not contiguous, that results in what we call external fragmentation, right? And that's the same thing that you can have with contiguous allocation also. Is that clear? That you can also have the same problem with contiguous allocation, that you have you've got these free space which says I have one free block here and I have another free block here, and but they're not contiguous. This guy and this guy, and they're not contiguous. They are two different locations. And if I want and if this guy is taken and this guy is taken, and if there's a new file request that says I want two cylinders, I don't have the ability to allocate that because this is the data structure that I've got, right? And so that becomes an issue, right? Is that idea clear? How this, the same problem that we saw with fixed size partition occurs again in contiguous allocation on the storage. So memory management and storage, there's a lot of similarity in that sense. So we can fix this, and in particular, what we want to do is, you remember one of the figures of merit that I mentioned before is efficiency of space utilization, right? What this means is that we want to reduce both internal and external fragmentation, right? So you want to do that, and in the context of memory management, what we did was we said let's assume that the operating system, the physical memory is composed of pages, and so we'll make page the unit of allocation. And once you have that concept, then I can say, well, I can get rid of external fragmentation altogether, right? Because now I'm going to, if you ask me for 8K, 16K, and my page size is 4K, I just need to give you 4 pages, and it doesn't really matter that they are not contiguous. Even if they are discontiguous, I can fix that in the page table data structure that the operating system keeps. That was a solution that we had in order to overcome external fragmentation. And just like in memory, I said that in memory, external fragmentation is the killer. You want to make sure that you don't have external fragmentation. Same thing is true in on the storage device also. You want to make sure that external fragmentation is not there. And therefore, what we're going to do is we're going to say, well, let's just like a page, let's think of what is the smallest granularity of allocation that you want on the disk. Okay, you can make it as small as possible as a sector, right? Can you go smaller than a sector in terms of storage allocation? You cannot, because it is the smallest unit that you can read and write on a disk is a sector. So, and from the point of view of contiguous access, you know that a file is going to be a little bit more than a sector, maybe at least a track, right? So you can say multiple sectors or multiple tracks or an entire cylinder or multiple cylinders, maybe the block, a block which is equivalent to a page. Okay, the size of a block is going to be in terms of multiples of either sectors or tracks or cylinders. Everybody with me here? Okay, so we're having this sort of an analogous thing to a page on the storage device, which we're calling a block. And so once you have that, that becomes the smallest granularity of access. Okay, and once you decide on block being the smallest granularity of access, if I wanted to allocate a file, and if it is more than a single block, what am I going to do? If it is more than a single block, I have to allocate a bunch of blocks for that, right? And if I wanted it to be flexible, as you pointed out earlier, you want it to be a list, right? A linked list is an efficient data structure when for growth of a file, right? Because an array is again size limited, right? So instead of an array, if I can have a linked list, then I can basically have a data structure for storage that mimics a linked list, and that's the next allocation that we're going to talk about, which is the linked list allocation. So here, so we've got two files, foo and bar, and so in the name table, which is the directory like a folder, okay, what you have is where is the starting disk block for foo, and I'm going to use the word disk block to mean some entity, logical entity, and this could be a multiple of sectors or tracks or cylinders. Okay, so and this is the unit of allocation. And once we have this unit of allocation, I can say that a particular file foo, the first disk block is this, and then if I run out of space on this, and if I have to allocate a new disk block, what I need to do is I need to know where is all the free blocks here. All these which have no pointers, they're free blocks, and so I can allocate from one of these guys, and this becomes the second disk block for file foo, and third disk block for file foo, and so now this file foo has three different disk blocks that make up the entire file. Okay, and the way we remember this, the data structure for remembering this is that what is the starting address for the disk block, and the rest of the information is in this itself. So there is data associated with foo is here, and also the next pointer for the next disk block that contiguously follows this is in this disk block as well. So that's a linked list allocation. And so how do you, what is the free list of sectors? That's another linked list. Just like in the case of page-based memory management, we have a free list of free pages. You're going to have a free list of sectors or free list of disk blocks that from which you can allocate anytime you want to allocate a particular block to a file that is growing. So Drew has been signaling for time. So let's take a short break, and then we will restart again and complete this file allocation. We will do PRS, but I want to finish file allocation for sure before we do that. So the idea in linked list allocation is that basically what you're doing is to start with, think of the entire disk as if there is nothing on the disk, then you have a gigantic free list, right? Which is a connection of all the blocks that are unallocated. And as you start making requests for storage space, you get it from the free list, and then give it to the file that's growing. And that's the idea behind linked list allocation. And now we can ask this question: how will be sequential access in with this kind of an allocation? Growth is good, right? Growth of a file is good because you can always grow a file by allocating a new disk block that when you run out of room in the current disk block that you have for foo. So that is good. What are the other figures of merit? We said sequential access and random access. So how do you think sequential access is going to be? Yeah, so is it good or bad? It could. We have no way of telling that, right? Because you start with that's what Peter was mentioning, fragmentation, right? So when you allocate, you're gonna have the situation where you're allocating this disk blocks for a file as it grows, and eventually you'll find that you're actually going to be necessarily jumping across blocks that are on different cylinders, which means that you're going to pay for access time to the disk, and therefore contiguous allocation is not going to be very good for linked list allocation. It's good within a particular block, right? It's still contiguous if especially a disk block is multiple cylinders or at least a cylinder. So long as my access is within a cylinder, I'm good, right? But the minute I'm going to grow the file beyond a disk block, then I run into the situation that it may not be very good. So contiguous allocation is a problem. What about random access? It's still sequential access is still okay, except that it is jumpy, right? But still it is okay. It is not as good as contiguous allocation that we saw earlier, but it is not terribly bad. Okay. But what about random access? Is it good or bad? Why is that bad? Well, more. Pardon your French. So Ryan, what do you think is bad about linked list allocation for random access? See, the thing is, with random access, what we really need to know is what all cylinders I may potentially, disks, blocks that I may potentially access. I don't have that information, right? In order to get what is the next disk block, I have to read this disk block, right? Because the pointer for the next disk block is contained as part of this particular disk block. So in order to know, in order to do the search, I have to go from here to here. I need to read this whole disk block to get to the pointer. Then only I can go to the next one and so on, right? And that is one of the inefficiencies of this linked list allocation. Okay, the fact that random access is going to be pretty bad, and the fact that you're building this linked list out of disk. I mean, one of the things that I want you to remember is that for file system that we're building, the data structures that the operating system needs to maintain are actually data structures that has to be on the disk because this is persistent, right? It has to survive power down and rebooting and system crashes and so on. So in that sense, these data structures that the operating system maintains are all persistent data structures. So this data structure better not go away, right? Because if you reboot the machine and if you don't have this data structure, then you're completely hosed, right? So you need the data structure to be persistent. So all of these data structures that we're talking about are on the disk. Free list is on the disk, and this linked list that says this is the set of blocks that foo has, this is a set of blocks bar has. They're all on the disk, okay? And what the operating system would do though is, as you access this data files, it will actually bring it into memory, and it will have in-memory copy of these data structures for efficient access. Okay, so for instance, if I am starting to access file foo, I am repeatedly accessing it. It will say, well, file foo is being accessed, and therefore this table I'm going to move it into, copy it into memory, right? And it is only a snapshot. I mean, if you don't create any more new files, then this contents of this table doesn't change. Is that idea clear? Right? So long as I don't create new files, the content of this table doesn't change. So you have in-memory data structure that is a mirror of this data structure that is on the disk. Okay? And as you create new files, then you're going to make new entry into this table, and you're also going to update this data structure which is in the disk, so that even if you power it down, your memory goes away, your disk is containing all the persistent files that you've created. Okay, everybody with me here? Any questions on that? Right. So now the problem is that if I have let's say that the file system doesn't grow. These are the set of files that I have in my system. I bring this into memory. Okay, I bring this into memory, but all I have about file foo is the starting disk block address. I don't have all the disk blocks that this particular file is actually occupying on the disk, right? And so if I need to know what is the disk block after this, I have to really go and read this disk block from the disk. Then only I can get the contents of that and then say, here is the next disk block from here on. Okay, that's one of the problems with this linked list allocation. And you heard this terminology FAT, F-A-T, FAT. What is FAT file system? Have you FAT allocation? Vladimir? Have you heard of FAT? Okay. What does it stand for? Anyone know? File allocation table. Is it a guess or is it? Is it? Okay. So FAT stands for file allocation table, and the idea is, you start. I said that to start with, this free list of blocks can be a gigantic linked list. Now at the beginning what are all the disk blocks available. So if I have, let's say, decided that a cylinder is a unit of allocation, if I have 1,000 cylinders in my disk, then I can have a data structure which says, there are 1,000 cylinders 0 through 999, let's say, and each one of them I can put a bit that says is it taken or not taken, right? And so essentially what I can do is I can actually have a link, do the linked list, but I can have an array representation of the linked list, right? That's what file allocation table is. Is that idea clear? Right? The idea being that a linked list, you have to do traversal in order to get the next pointer. Instead, if I have an array, then I can say that an array is a representation of the linked list, and that's what file allocation table is. And so what you have now is this data structure. Once again, this data structure also has to be in memory. I mean, it has to be on the persistent store, right? So this is yet another data structure that I'm calling file allocation table. And what this says is, for this particular file foo, I'm going to say what are all the disk blocks that correspond to this particular file. I'm going to say, well, disk block 30 is the first disk block, and so this this particular entry is saying whether the particular disk block is taken or free. So initially everything is free, and as you start growing a file, you say, well, this file is going to grow. I'm going to allocate a new disk block. Let's say the next disk block I'm allocate is going to allocate is 70. Then I say that the next pointer is 70, and so I'm basically having an array representation for the file allocation that is happening as a linked list, right? And so now if you look at file foo, it's a linked list that contains a block number 30 and block number 70, and this I can get entirely from this table. I don't have to go to the block read block number 30 in order to find out that the next pointer is 70, right? I've sort of abstracted that into this table, and now what I can do is, if in the operating system, in addition to caching this in memory, I can also cache this entire file allocation table into memory, and therefore once I have it in memory, then I immediately know if I look at file foo, I'll know all the disk blocks that particular file foo has by looking at this in-memory data structure. Okay. So I want to make sure that you understand the concept of in-memory data structure and persistent data structure, and I'll quiz you on that at some point of time. So the basic idea being that you want persistent data structure for things that are long-lived, which are files, but for efficiency purposes, you want to have a snapshot of the data structure in memory, and you want to keep the two consistent. Every time you allocate a new file, then you have to go and look at this file allocation table and see what disk blocks are currently unallocated, and then make allocation for that. So you basically are building a linked list using this file allocation table and in an array structure, and you have to have a distinguished value that says that this is the end of the file. So you might use -1, for instance, to indicate that this is the last block. 70 is the last block in file number file foo. So it consists of 2 disk blocks, 30 and 70. And on the other hand, file bar has a single disk block because the next pointer is -1. Shane? I'll get to that in a minute. Yeah, Jen? Right. So now that comes back to this question. So I'll talk about that. So the file allocation table is saying I know the full capacity of the disk. I know that my disk is let's say 60 gigabytes, and I'm going to say that my unit of allocation for file smallest granularity is, let's say, a megabyte. Then you can do the math and figure out how big this table is going to be, right? Because you need an entry for each one of the disk blocks that you have in the entire file system, right? And that is this file allocation table data structure, okay? And we'll talk about partition and FAT32 in a minute. Joe? Oh, so that's an interesting question, right? So we have to worry about crash recovery. So for now, let's not think about it. We'll come back to that later on, okay? So for now, we're assuming that bad things don't happen, and so what we're doing is we're saying, well, there is a data structure on the disk, and if I have to go to the data structure all the time for every file access, it is inefficient. I'm going to keep a copy of that in memory, and that memory copy is the snapshot of what used to be there, and now if I make modifications, then I have to reflect that on the disk in order to make sure that I cover myself if there is a crash. And there can be window of vulnerability when I've made the change to the in-memory data structure, haven't done that to the disk, and the system crashes, right? So it can happen. Okay? So we'll talk about that later on. But that's the basic idea. And so so let's talk about the figures of merit here. So what about sequential access? Is it good? Sequential access is the same as a linked list allocation, no different, right? Because it is, it can be slightly faster, but not significantly faster, because you're going to read the whole disk block number 30, and then you're going to go on to block number 70. And so in terms of sequential access, it's not going to be any different from a linked list, true linked list allocation, right? This is just an array representation of the linked list, but it is going to have the same performance characteristic. What about random access? Random access can be much better, because now all the disk blocks that correspond to file foo is now available in this data structure, right? And you can have algorithms that efficiently manipulate this data structure in order to access what you're looking for and so on, right? And that is the nice thing about the file allocation table. What are the bad things about FAT? Pardon me? Well, yes, for holding the data structure, right? So not just the memory, but it's actually taking up space on the disk also, because the FAT itself is a data structure that has to live on the disk, and so you are having a space overhead for this file allocation table, right? But you're saying, well, from the point of view of the high-level figure of merit of contiguous, good contiguous access and good random access, I'm willing to pay a little bit of overhead for space. Joe? That we have agreed is going to happen, right? With once we have this, just like paging, we've said that okay, we're going to do a disk block as a unit of access, unit of allocation, and therefore we're going to pay for internal fragmentation. And this is where you will decide what is the right size for a disk block. Should it be a multiple of sectors, a multiple of tracks, multiple of cylinders, and so on. So you're bounding the amount of internal fragmentation by making that choice. But that choice comes at the size of this table, right? The smaller the granularity of a storage allocation, the bigger this table is going to be, the bigger the space overhead for keeping that. Same problem that we had with page tables, right? So with page tables also, you can make the pages as small as you want, but if you make the page too small, then your page table becomes really big, right? And so there is a tension between efficiency and overhead for storage. So that is the fat data structure. And as Jim pointed out, so he said, what is a partition? What is a partition? So the point is that there are these there is the Microsoft Windows is the one that came up with this fat allocation scheme, and initially you heard of fat 16. Okay, do you know what that is? So the 16 pertains to how many how big is the disk address? Okay, and so if the disk address remember that, what is the disk address again? How do you say what a disk address is, Shashank? Do you remember what is the disk address? Well, but what exactly is the the representation for a disk address? Shane? You have track, sector, more than that. You have platter, right? So you have platter, a surface, and a track, and then a sector, right? This is what a disk address is. And FAT32 says how many bytes is used to represent a disk address. Okay, and so when you decide that, what is it that we are deciding, Brad? Yeah. FAT16. I think it is number of bits that it's the number of bits or bytes. I should look it up. My bit sounds too small to me, but byte also sounds pretty big to me. But yeah, so the surface is pretty small. No, but I wanted to see how big is. That's a good question. So I forgot. So let me look it up. Pardon me? 16 bits? Okay, there you go. So the 16 bits is what is being used as the disk address. And so when you're using 16 bits, your disk block address is 16 bits, right? And how big is how many disk blocks can you have when you have 16 bits? No, disk blocks. How many disk blocks can you have? 2 to the 16, right? And so depending on the granularity that you chose, you multiply it by that. That gives you the total size of the disk, right? So let's say that our 2 to the 16 is 16K. Is that 16K? 2 to the 64K. So 64K, and if I say that I have a megabyte for each disk block, how much is the total capacity of the disk now? 64 times 10 to the 9, right? So it is so that gives you the size, right? So that is the maximum size of the disk that I can have with FAT16. Is that idea clear? So the minute I say 16-bit address, and if I specify the granularity of a particular disk block, that gives you the maximum capacity I can have for the disk, right? Now disk size keep growing, right? Because the new technology you get, from, if let's say that I had a 32 gig disk and my FAT16 was living in that. Now I get a new disk drive that has 60 gigabytes. Now what do? My file system can only be as big as the FAT, and if it is 16 and it can access 32 gigabytes, now I have a 60 gigabyte drive, I cannot access the remaining, right? And that's the reason that you've got partitions, which basically says that now let me break that physical disk into multiple logical partitions, and in each logical partition I'm going to have a fat file system. Okay, so on your drives you may have seen you have, if you have Microsoft Windows, you have C drive and D drive and so on. You may be having a single hard disk, but it is actually keeping that as distinct logical drives within the physical disk. Okay, and the reason why that came about is because of the limitation in the addressing FAT16, that the size of a disk block, the address for a disk block was 16 bits. Okay, now FAT32 said, well, that's a limitation, let's make it 32 bits. Make the disk address 32 bits, and that way you can grow the file system to be bigger than what you can get with a FAT16 file system. Okay, that is FAT32. Okay. So the out of that 32 bits, you might say 1 bit is reserved for, so that's a 32-bit address, right? So you have a way of partitioning it, and there is a partition table that we'll come to later on. But given a partition, this is the address for a disk block within that partition. Now, how do you know which partition it is? There is a partition table. We'll talk about that later on. Not taken out as 16 bits or 32 bits. Jen? Well, the hardware the hardware fixes certain things. The software fixes something else, right? What hardware fixes we've already seen. What are the things that the hardware fixes? A number of tracks, a number of surfaces, and number of sectors, and how big is a sector in terms of number of bytes. So those are the things that the hardware fixes. And it may also fix the recording density. So you might say that all the sectors contain the same amount, all the tracks contain the same amount of sectors, or you may have variable recording density where you say zone bit recording. All of these are hardware parameters, right? Now what we're talking about is the software parameters. A disk block is a software entity that is saying it's going to be a multiple of what the hardware provides me. It could be multiple of sectors, multiple of tracks, multiple of cylinders, and so on, right? But the key point that I want to get out of this file allocation table policy is that you can either have, you're fixing the size of the maximum capacity of the disk that you can manage with a single FAT, depending on the addressing of the disk address. If it is 16-bit, then it fixes the size to be something small. 32 bits, something bigger, but still it is bounded, right? That's the idea behind file allocation table. So the next thing that so that's the limitation that file allocation table has, and the reason why there is a limitation is because there is a single data structure for the entire file system, right? This data structure is not for a particular file, but it is for the entire file system, right? And so one way to break that is to say, well, how about I take this fat data structure, which is a centralized big data structure, partition it, keep it one per file. Okay, and if I keep it one per file, then I'm no longer bounded by the maximum size of the disk itself, but it is now coming back to a single file. That's the idea behind what is called indexed allocation. Indexed allocation, you can simply think of it as taking this fat data structure and breaking it up into individual tables, one per file. So, and you've heard the term inode, right? Have you heard of the term inode, any of you? Okay. Inode comes from Unix terminology for the data structure that maintains information about a particular file, and I stands for index, obviously. So it's the index node for file foo. And so basically, what you have in the index node is this address, this the directory that we keep talking about, the directory says where is the inode, the index node for this particular file foo. And the index node is nothing but another disk block, okay, which you're using for keeping this metadata, right? The metadata being what are all the blocks that foo is using. So in this case, it uses two blocks. One block has the disk block address 100, another one has 200, 201. So these are the two data blocks that is associated with this file foo. Okay, everybody with me here? So this is, it's sort of like, if you have you have a yellow pages, you flip to section R to look up my last name, and within that you can then say, well, where is my phone number, right? So that's the same sort of thing that this is doing, which is saying this is the inode for this particular file, which sits at disk block address 30, and the contents of this inode tell me what are all the data blocks that this particular file contains. And similarly, if you look at the inode for bar, it's at disk block address 50, and the contents of this inode is going to say what are all the data blocks contained. So in this case, there's only one data block, 99, and there's nothing else. So here again we have the array structure, right? Similar to the fat allocation table, we have the array structure, but the array structure is per file. Okay, and therefore you don't have a bound on the fat data structure. So fat data structure was for the entire file system, but now for every file I have this table that is allocated, and this table contains information about that particular file. Okay, and that gives you the ability to sort of decouple the maximum size of the storage system from the data structure that you maintain to access and allocate storage on the disk. Jen? We'll come to that. Okay, so but I want you to get the concept of what this inode is. Basically, if I say that a file cannot, so in this case I have 3 entries here, right? It's almost like contiguous fixed allocation, right? In the sense that I'm saying that you cannot have any more than 3 data blocks associated with the file, the way that I've shown this picture, right? And so this inode contains 3 blocks, and Jin's question is, well, how do I decide how big is the inode? We'll talk about that as the next thing. Any other question before? What is the time now? Pardon me? Oh, okay, so maybe we should stop, huh? Okay. All right. And you have a party coming in, so that's another reason that I have. So we have one more thing to talk about, which is multi-level indexed allocation that will answer Jin's question. So I'll take probably half an hour on next Tuesday to talk about the rest of the story on file system, and then maybe on Tuesday I'll also do a show and tell of some generations of hardware that over the last few decades.